Hi and welcome back. So let's take a look first at some simple examples using the dunder add, dunder sub, etc. Let's say that we want to implement a vector class that supports these various arithmetic operations. Now I'm not going to assume a specific number of dimensions here. That's basically going to be determined by how many arguments I'll pass to the dunder init method. So I'll make these vectors to be an arbitrary dimension. But I will, however, require the arguments to be real numbers. So we're kind of building on what we were doing in previous sections. So the first thing is I'm going to import from the numbers module, I'm going to import the real, because I'm going to use that to test if the inputs are instances of real numbers. Okay, so let's create our vector class. So for our vector class, we're going to do an init, and I'm going to allow an arbitrary number of arguments, of positional arguments, to the init. That will determine the number of components basically in my vector. But I do want to do a few checks. Firstly, I want to make sure that the components is not of zero length. So if the length of the components is less than 1, then I'm going to raise a value error, and I'm going to say cannot create an empty vector. Next, I'm going to check that every component that gets passed into components is a real number. So if not, is instance component real. Okay, then again, I'm going to raise a value error. So I'm going to raise value error, and let me fix this typo here. And I'm going to return the message something like vector components must all be real numbers, something like that. And if I wanted to, I could actually specify which one is causing the problem. So we could do an interpolated F string and just say component is invalid, like so. Okay, so we could even do something like that. Now, as long as this is all fine, then my code will reach here. And so at this point, I'm okay storing the value, and I'm going to put that into a private variable. I don't want people to directly modify the components, so I'm going to do it that way. Of course, it's pseudo private. I'm also going to define a dunder len method. I want to support the len function, and so here all I need to do is just return the length of self._components. Now, the one thing I want to point out, sometimes I will do this, and you'll see that my code, for example, in the Jupyter notebook has that, because I want to make sure that components is a tuple. Now, it should already be a tuple, but just to be safe and just to be more explicit, sometimes I'll put that in there so that somebody reading the code understands that underscore components is a tuple, because they may not realize that when we have a variable number of arguments in the function, then the components that we have inside the function is already a tuple. Now, of course, this isn't going to create a new tuple if components is already a tuple. It's just going to reuse the existing one. So now that I've got that, let's go ahead and define the components property. So we'll use a property decorator, and I'm going to create my components property. And then here, all I'm going to do basically is return self._components. The next thing I want to do is I want to implement the representation for this class. So let's implement the repr method, and let's do this one. Now, this is going to work, but it's potentially a little unwieldy, because what I'm going to do is I'm going to grab the components. So I could either grab them using the property or using the underscore components, the private backing variable. So I'm going to do that. But now if we have a vector that has 100 dimensions, then this is going to be a long representation. So this works, but there's probably better things that we could do. And then I need to make sure that I also put in my parentheses to try and get a proper representation. So we could try our vector out at this point. We can say let's say v1 equals vector, let's say 1, 2. And let's say v2 equals vector 10, 20, 30, 40, for example. So now I should be able to look at the length of v1 and the length of v2, since I've implemented now the dunder len method. And as you can see, we get that, 2 and 4. I can look at the representation of v1, and I can look at the representation of v2. And it looks like I didn't need those parentheses because the representation of a tuple already includes the parentheses. So I'm going to remove them from my representation here. Let's run through this again. That's better. Vector 1, 2, vector 10, 20, 30, 40. Okay, so that seems to work. And of course, if we try and call string of v1, then it's still going to call the wrapper method since we didn't implement the dunder string method. Now let's go ahead and let's support addition and subtraction of vectors. Now, in order to add and subtract vectors, we'll require them to be of the same dimension, right? We cannot subtract a two-dimensional vector from a four-dimensional vector, for example, or add a three-dimensional vector to a one-dimensional vector. So here my implementation is going to require the vectors to have the same length, essentially. So let's go ahead and do that. I'm going to take this code and paste it down here, and let's start adding on to our class. So the next thing that I want to do, therefore, is implement those methods. So let's implement the add method first, and we'll receive the right operand in other, right? So self is going to be the left operand of the plus operator, and other will be the right operand. So what I want to do here is I want to check whether other is of the same type. In other words, is it a vector? And moreover, is it of the same length? Now I'm going to need to do that in other places as well, like in the subtract, right? In the dunder sub method, I'll need to do the same thing. So here I'm actually going to create a method called validate type and dimension. Okay, and basically it's going to take the current instance and it's going to take another vector v, let's say. And all I'm going to do here is return, well, is it an instance? So is instance v comma vector. So is the other one, basically, is it an instance of the vector? And the length of that vector is equal to the length of self. Now, I could have written this method as a static method that takes in two vectors, right? And then here I would call the static method. Or I could have defined this outside of my class. I just chose to do it this way, but feel free to implement it however you want. There's more than one way of doing it. So now, though, I am going to call it. I'm going to say if not, self.validate type and dimension, passing in the other vector, or the other argument, which is going to be the right operand. So that's going to check, and that's going to return true if the things match, if it if it has the properties that I want. Otherwise, I'm going to return a not implemented. So I'm going to say no, for these two operand types, that is not going to be allowed. That's not going to be implemented. So now I'm going to make my new components, right? So remember, the addition is going to return a new vector. So here I'm going to basically create my new components. So I'm going to say this is x plus y for x comma y in, and I'm going to zip up my self's components and the others components, right? So I know that other has components because it's a vector. It passed this validation. So I'm going to zip up the two sets of components, and I'm just going to add them pairwise. And then I'm going to return a new vector that's going to be initialized with the contents of components. So now, of course, I have to unpack components into its separate arguments. So this will create a new vector. Now let's go ahead and do the same thing now, but for the sub. So dunder sub, self other, and basically it's very similar. So I'm just going to copy this code and I'm going to paste it over here. The only difference is that I'm going to subtract one from the other. I'm going to subtract the right operand from the left operand, and then just return the vector. So that's our class. That should be it. We've implemented addition and subtraction. So let's try it out. Let's create a few vectors. Let's say v1 equals vector 1 comma 2. Let's say v2 equals vector 10 comma 10. And let's say v3 equals vector 1, 2, 3, and 4. Right? So v1, v2 have the same dimension. So as before, we have the representation for v1. We can add v1 and v2. We'll get a new vector. And this is the representation for the new vector, 11 and 12. That seems correct. We can, of course, do v2 plus v1, right? We get exactly the same result. That's commutative. But let's go ahead and do this. Let's say v1 plus v3. And as you can see, now we get our type error. We have an unsupported type. So this error message might be a little misleading. It's saying, well, we don't have a supported type for vector and vector, but that's not really because of that. It's because we have vectors of different dimensions. So if you wanted to, you could actually create a custom error that maybe inherits from type error, and then you could then, bring up a custom error. So let me show you what I mean by this, and we'll get into custom exceptions later in this course. So I'm not going to explain this too much, but maybe this is a vector mismatch, vector dimension mismatch. Okay, and I'm going to inherit from type error. So again, this may seem a little foreign, but we'll see later. So now that I have this, instead of returning the not implemented here, what I might do is raise a mismatch or a vector dimension mismatch and saying, vectors must be of same dimension, something like this. So we could do that instead if we wanted to. And so we can do that here and here as well. And so now when we run through this, everything works fine. And then when we try the v1 plus v3, as you can see, now we get a vector dimension mismatch exception. Vectors must be of the same dimension. And I guess I should fix my typo, must. Now, why inherit from type error? Well, because now there's two ways we could catch errors here. We could say try, and we could say v1 plus v3, and we could say except. And of course, we can definitely catch it as a vector dimension mismatch as ex, print ex. Okay, so we get that. But we could also catch it as a type error. If we have something that's maybe a little more generic, we could also catch it as a type error, and it will catch it. Vectors must be of the same dimension. I thought I had fixed that. So let's rerun this definition and run all that. And there we go. Vectors must be of the same dimension. So how you want to do it kind of depends. I jumped ahead a little bit here showing you custom exceptions, but we'll come back to those in detail. Now, of course, we could also try to do something like this. Try v1 plus 100. And I'm not even going to catch it. I'm just going to see what the exception is. Now, of course, right now, we're going to get our custom exception. Vector dimension mismatch. Vectors must be of the same dimension. So now I have another problem, right? This error message is misleading. So in order to do exception handling properly here, we'd have to get a little bit more complicated. So I'm going to go back to just returning not implemented. Because when I have that, that's a little misleading when I have two vectors that are not of the same dimension. But it's not misleading in this case over here. Okay. So I want to keep it simple. So for now, I'm just going to go back to this very simple thing. So here I'm just getting a type error, unsupported operand type for vector and int. Okay, so now let's go ahead and implement the multiplication by a scalar value. So I'm going to go back, copy this code, paste it down here, and let's keep expanding on our class. So let's go ahead and write the mul method. So this is going to be a method that's going to be bound to the instance self, and then we'll be, of course, getting the second operand, the right operand, in the other argument. So here I'm going to put in a function, a print, I should say, call, just to say mul called. Okay, just so we can see that this method was called. And here I'm going to say if not is instance. And I want my other to be a real number. I want it to be a scalar, a real number. If it's not, I'm going to return not implemented. And then here, I'm going to make my new components. So components equals other times x for x in self.components. And I'm going to return a new vector with my components as the arguments for the init. So that's implemented the multiplication. Let's go ahead and try it out. So we can say v1 equals vector, and let's say 1 comma 2. And let's say we do v1 times 10. And as you can see, the mul method was called, and now we have a new vector with values 10 and 20. But what happens when we try the reverse operation, right? So I had v1 times 10. What did that actually do? Well, that called v1 dunder mul, right? So it's calling the mul method bound to v1, and then in addition we pass in 10 as the argument. So that's exactly what we did over here, right? This ended up doing this call. But what happens if we do 10 times v1? Well, now we get an exception. So we get this type error. And basically you can think of it this way. When we did 10 times v1, Python tried to execute something that might look like this. Now, integers are built-ins, they don't have this add method, but basically it tried making this kind of call. And the integer class is saying, well, I don't know how to deal with multiplication times this custom class. So it returns a not implemented. Now at this point, what's happening? Well, we have a not implemented returned from the integer class, and this type here and this type here are not the same type. So Python is going to use reflection. So Python is going to try v1 dot, but it's not going to call the mul method, right? It's not going to do this, right? It's actually going to call the rmul method, the right multiplication, because it just did that flip, right? So it went from 10 times v1 to v1 times 10, but it still needs to keep and tell us which was the left operand, which was the right operand, because sometimes that's important since not everything is commutative. So it's going to try and call this method. Well, our class doesn't have that method either. So now Python turns around and throws up this type error exception saying unsupported operand type, right, between int and vector. So all we need to do is actually implement this method in order to support this over here, right? Because what's happening is that Python will flip this, will reflect that to v1 times 10, calling the rmul method instead of the mul method. So let's go ahead and do that. Let's copy this class code and let's paste this down here. And all we need to do is implement the rmul method. Now, what is the rmul going to be? Well, it's going to call basically the 10 times v1 is going to be called as v1 rmul 10, right? So other is going to be 10, it's going to be the integer, and self is going to be v1 essentially. So I already have multiplication defined. So all I need to do here is return self times other. I'm going to return the vector, because that's going to be the vector, because it's going to be v1 dot rmul. So v1 is self times other, which is the integer. So that's all I need to do. I can just leverage the existing multiplication. So now let's try this. Let's say v1 equals vector 1 comma 2, and we can do v1 times 10, that called the mul method. I'm going to print another statement here. I'm going to say print rmul called, just so we can see that this method was called. Okay, so the mul method was called. Now if I say 10 times v1, you'll see that the rmul method was called, and of course we called the mul method after that because we're leveraging what's there already, and so the mul method was also called. So now let's say that we want to implement the dot product of two vectors. Now if you're rusty on this, I have a link in the Jupyter Notebook. You can take a look at the Wikipedia article on the dot product. But basically, to get the dot product of two vectors, they should be of the same dimension, and we just sum up the product of the components, pairwise basically. So we take the component 1 and 1 of the two vectors, multiply them, do the same thing for each pair of components, and then we add everything up. So we can implement this using the multiplication. So now we're going to have to be a little careful because we already have multiplication defined, right? So if we want to say v1 times v2, we're going to have to differentiate in here between real numbers and another vector, and then just change how this works. Now we won't have to worry about the rmul, because remember, the rmul is only going to get called when Python has to reflect the multiplication. But the multiplication will not be reflected when we're dealing with two instances of the same type. So that's not going to get called. We only have to worry about this one over here. So let's go ahead and implement that. So again, I'm going to copy paste the code. And now we're going to change our multiplication. So what are we going to do? Well, I'm not going to check if it's not an instance. I'm going to check if it is an instance. So if other is an instance of real, then what am I going to do? I'm essentially going to calculate this components, and I'm going to return a vector of those components. If I haven't returned, then I'm going to check again to see if I have the same type. So if validate type and dimensions with against the other argument, the other operand basically. If that's the case, then I'm going to do the dot product, right? So here I'm using the calculating the dot product. Here I'm basically calculating the scalar product. So how do I calculate the dot product? It's very simple. I can say components equals, I'm going to say x times y for x comma y in zip self.components and other dot components, right? So I'm going to zip up the components, multiply them, and then of course I have to sum them. So I can return the sum of the components. So the dot product doesn't return a vector, the dot product returns a scalar. So I'm going to return the sum of the components. If that's not happened either, then this wasn't multiplication by a real, it wasn't multiplying by another vector of the same dimension, so I'm going to return not implemented, like so. And then RML is going to stay as is. So now let's give this a shot. So v1 equals vector, let's say 1 comma 2, and v2 equals vector 3 comma 4. I can type. And now we can say v1 times v2, and that again called the mul. And as you can see, it returned 1 times 3 plus 2 times 4. So 3 plus 8, which is 11. So it calculated the dot product. Now we could also implement the cross product of two vectors, which does return another vector. The calculations get more complicated, especially when you have arbitrary dimensions. So I'm not actually going to implement this, but I'm going to show you how we could potentially implement it using the at operator, which is the matmul operator. So let's go ahead and copy this code, and I'm going to paste it down here. And now I'm going to define the matmul operator, self and other. And of course I could put the checks in. Is it another, is other also a vector? Is it of the same dimension? Blah, blah, blah. And then actually implement how to calculate the cross product. Instead, I'm just going to print out matmul called. Okay, like so. So it's not actually going to return anything. So now I can create two vectors. So let's say 1 comma 2, and let's say v2 equals vector 3 comma 4. And now I can say v1 at v2. And so this now operator is going to call the matmul special method, the dunder matmul method in our vector class. Okay, so the next thing I want to talk about are the in-place operators. So the in-place operators typically mutate the objects. When you have mutable objects, they typically mutate the object, right? So for example, if I say L equals 1 comma 2, so I'm making L a list. Now let's take a look at the ID of L. You can see it's that number. Now what I'm going to do, I'm going to say L plus equals, let's say 3, 4. Now this is an in-place operation. This is a mutating operation on L. If I look at the ID of L and L, well, first of all, you can see that L has been mutated. Well, at least we have now a list that contains 1, 2, 3, and 4. But you'll notice the ID of L has not changed. So in fact, L was mutated. That's not the same thing as saying L. Let's start again. L equals 1, 2. And let's print out the ID of L. Then I'm going to say L equals L plus 3, 4. Okay, and now I'm going to print the ID of L and L. So again, the end result, L now is a list, 1, 2, 3, 4, but you'll notice the ID has changed. Okay, so that's the difference between an in-place operation, like a plus equals, and this over here. Now, I just want to point out also that in-place operations does not guarantee a mutation. We have immutable objects. Tuples, for example, are immutable. So if we do the same thing with a tuple, 1 comma 2, I can print the ID of t, and then I can say t plus equals, let's say 3 comma 4, and then I'm going to print again the ID of t and t. Print. the ID of t and t, then as you can see, the new tuple is 1, 2, 3, 4, but it is a new tuple. It is not the same object, even though I used an in-place operator. So in-place operations don't have to mutate. In fact, for immutable types, it can't, so it has to return a new object, right? But in general, for mutable types, the in-place operations will perform a mutation, which is why we have something that's different. We don't just have the underscore, the dunder add method, we have the dunder iadd method, so that we can actually implement this operator over here. This plus equals is an operator that takes two operands, the left operand, the right operand, and returns something. In some cases, it will return the left operand mutated. In other cases, like here, it will just return a new object altogether. So let's go back to our vector class and implement in-place addition. That's very straightforward. So let's take this class, let's paste that in, and let's implement our iadd method. So def underscore iadd, self and other. Okay, self will be the left operand, other is the right operand. I'm just going to again say add called, so we can see when it's called. And then all I'm going to do here is I'm going to return self plus other, right? So I'm going to leverage the fact that I already have the add defined, and I am returning a new vector. So we can then try it out this way. Vector 1, 2, and then v2 equals vector 10, 10. And let's print the ID of v1. We just need v1. Now let's go ahead and say v1 plus equals v2. So v1 equals v1 plus v2, but using the iadd, using in-place addition. And now print ID of v1 and v1. Okay, so as you can see, our new vector is 11, 12. So it did the addition, 11 and 12, but as you can see, our add was called, and we now have a different object for v1. So it's not like the original v1 was mutated. So let's modify this so that it does mutation, just to show you how we would do something like that. So let's copy and paste this code in. So all I'm going to do here is do pairwise addition of the components, which means now one thing that I didn't have to check over here was the size, right? The dimension of the two things, because I call the add method that already does this validation over here. So I'm going to need now to do that because I'm not going to call the add method, which is what this did. So I'm going to replace that and just test. Make sure that I'm dealing with two vectors of equal dimension. So we could do that. I'm going to actually just say if it's true, right? And if it's not true, I'll return not implemented. But if it's true, I'm going to look at my components basically and say x plus y for x comma y in zip self.components and other.components. All right, so now I have that calculation done. What do I want to do with those components? Well, I just need to replace self._components, right? I can't assign it using the property because I made a read-only property, right, over here. So I have to use now the private variable. So that's all I'm going to do. I'm just going to say that's equal to. Now I do have to make that into a tuple because right now this was just a generator, right? So I'm going to convert that generator to a tuple and replace my private variable. And then I shouldn't forget to do that. I need to return myself, right? Because the plus equals needs to return something. So I'm going to return myself. Okay. So now that that's done, let's go ahead and see the difference. I'm going to copy paste this code over here. Remember what happened? We had a new vector, right? That was the result. So now if we do this, you'll see that the vector has stayed the same. We still get now 11 and 12, but v1 has been mutated and now it has components 11 and 12. So let's go ahead and implement also the unary minus on our vector class just for another one. So let's copy paste this code. Let's go in here and I want to basically define the unary minus, the negative, right? So the dunder neg method, and of course it only has a single operand, the object that it's bound to itself. So let's go ahead and say print neg called. So the negative function was called. And again, I'm just going to use this approach to do that. So I'm going to say minus x for x in self.components. And then I'm going to return a new vector using the components that I just did here. Okay, like so. So again, negation is not doing a mutation of the vector, it's returning a new vector. So let's try it out. We get vector 1, 2. And now if I do minus v1, and let's look at the ID of v1, and let's say v2 equals negative v1, like so. And as you can see, the negation was called. And if I look at the ID of v2, well, that is not the same. So this was a new vector. But the contents of v2 is negative 1, negative 2. Just the negative of each component. So you can even say things like this. You can say v2 equals vector 10, 20, right? So we have v1 and v2. And then we could say v1 plus negative v2. That would work just as well. And now, of course, it's going to negate v2. So it's going to be 1 plus negative 10 and 2 plus negative 20. And then lastly, let's implement the absolute value. So we don't have the absolute value of our vectors at this point, right? There's a bad operand type for ABS. So let's go ahead and fix that by essentially implementing the dunder-abs method. So let's go ahead and implement that method, dunder-abs. And of course, it's a single argument, just the object itself, the instance itself. And I am going to need to import the square root. So let me say from math import sqrt. Okay, I'm going to need the square root function from the math module. And all we're going to do here is return the absolute value. So let's go ahead and just print abs called. And let's go ahead and return the square root of the sum of the squares of the components. So of x squared for x in self.components. Okay. So that's the absolute value defined. So now if we have this vector 1, 1, then we should expect the absolute value of v1 to be square root of 2, right? 1.414. Okay, so this gives you kind of, a good look at how we can implement a lot of functionality for the existing operators in Python and basically provide this polymorphic behavior by using these special methods, these dunder methods. Again, I'm going to reiterate here, don't use dunder naming conventions for your own functions and your own variables and so on. Leave those for Python. You never know what it's going to use in the future. Now, the other thing too is that these arithmetic operators are not restricted to working with numbers, right? We've seen them work with strings, for example, or even lists, right? We have, let's say, a list 1, 2 times 4, right? We know that this multiplication operation isn't limited to just numbers. It can work with other things as well. And in particular, with our own classes, we can implement, multiplication and addition and subtraction in our own classes, even if they're not numbers. They don't have to be numerics. A vector isn't really a number class, although it uses numbers, right? So it's kind of related to numbers, but we can go totally outside of numbers. Let's take a look at a very simple example. I'm going to talk about a family and person. So a family is going to have a few properties for the mother, the father, and the children. And each of those are going to be person objects. So let's go ahead and write our person class. So self, and then we'll just have a name. We'll keep it simple. We'll use a bare attribute for the name. And then we're going to also write a representation. And usually I always write a representation because having a representation that tells me the state of the object is much more useful than just knowing the memory address of the object. So usually I always write that. So I'm going to use an interpolated string and we'll say this was a person object and it's self.name. Okay, so this is how we're going to represent the class. So if I say P1 equals person, let's say John, then I can look at the representation of P1 and I have that. Okay, now let's go ahead and define this class, family. So now I'm creating another class and in my init, I'm going to pass in the mother and the father. And I'm going to store those as instance attributes, their attributes. and self.father equals father. And then I'm also going to create a new attribute called children, and that's going to be a list that's going to be initially empty. Then I'm going to define an in-place addition, I add. So I'm going to create this I add, and it's going to receive another thing, and I'm going to have self.children.append other. So I'm not checking for types and so on. We could probably do that, but here I just want to keep it simple. Okay, so I have this family class that supports the I add. Now family is not a number, right? It's basically an object that contains properties or attributes that themselves are other types of objects and so on. And here now I'm going to create a new family. So my family needs the mother. So let's say the mother is Mary, and let's say that the father is John. Okay, so now I have a family with those two attributes set. And let me fix the typo. Right, so I have f.mother, I have f.father, and I have f.children. Okay, so we get person Mary, person John, and we have no children. So now what I could say is I could say, well, to add a child to the family, I can just use in-place addition. I can say family plus equals person Eric. So if I do this, you'll see now that if I look at f.children, now the children contains Eric. And I can continue. I can say f plus equals person Michael. And so this is just going to keep adding to the children. As you can see now, we have Eric and Michael. So don't feel that you're restricted to numerical types when you're using these arithmetic operators. You're not. Just, be creative. There might be a very, good reason for using addition between, two object types that have nothing to do with numbers, as we saw over here. That was maybe a little bit of a stretch, but there might be other instances where that does make sense. All right, thanks for watching, and I'll see you in the next video.